There's a few people in Zoom right here. I can see them right away. Guys, let's go ahead and get started. Welcome to a new week and a new day. I hope that you had a good weekend and everything is going smoothly for now. Couple of comments here as we get started. I'm not gonna go over the, well, I went over the quiz, I guess, after the quiz on Thursday. If you have any questions about your specific quiz, you can ask me about that in office hours or over email. I'd be happy to try to clarify that a little bit. But anyway, as long as I've got you here in the front row, I can easily pass this back. I wanted to pull up our Canvas course page for a minute. Does this Canvas thing, does it notify you guys every time I sort of tweak it a little bit?
Yeah.
So did you get a little notification that I messed around with the midterm folder?
I didn't.
No? Okay, well then I better show it to you. So over the weekend, we have a midterm, actually, it's 2 weeks from today. So it's coming up fairly soon. I decided that I should get this midterm 1 resources folder kind of filled up a little bit more nicely. So I wanted to go over what's in here with you. As you have time, you can start looking at it. First of all, I put the quiz, you might notice here, I put the quiz and the solutions to the quiz in here. So if anybody didn't get the answers yet, there's an answer key in there you can take a look at. But I also have 2 sample midterms. These are actual midterms that I've used in this class before. There's an all caps version, and then there's an all lowercase version. And for each of them, I also have the answer keys. And not just the answer keys, this actually worked out detailed solutions. So what I would actually recommend that you do, first of all, I would recommend that you don't just jump into the sample midterm if you haven't even thought about studying yet. I would probably wait until you've given a reasonable effort to studying. And then I would probably recommend that everybody should do, all of this is optional. Nothing here is required at all. But at a minimum, I would recommend that everybody try to at least sit down and do 1 sample midterm. If you do 1 sample midterm and you're not feeling so great about how that turns out, then what you might do is go back to some studying on whatever those weak points are, and then maybe try the other one. Because there are 2 completely different exams in here that you can practice on. How much or how little you're going to study for our test in 2 weeks kind of depends on you, how you're feeling, how comfortable you are with everything, and just how your whole life is as far as free time and, do you have the time to put into this? Because if you really want to, you can make a lot of hours out of this, because there's also a review packet here. Let me actually open that one up because it's got some information in there that I want you to be aware of. I'm just giving you a quick little tour of this folder, just so you have an idea. So you can see I've kind of talked about when the exam is and what it's going to cover. You can see it's going to cover chapters 2, 3, 5, which we basically are done with, and then also chapter 6, which we're going to start today. And I've already put down some extra office hours for the days leading up to the exam. I've got some weekend Fridays and Sunday hours there that I'll try to have for you. And then also some review sessions. What I'm actually going to do is show up and work out some example problems for you that would be similar to exam problems. Now, you don't have to come. If you can, that's great. It'd be nice if there was somebody in the room besides myself. But if I'm talking to an empty room, I will be recording it on my phone here. And I will also be available in Zoom. So if you want to come in live through Zoom, which is what some students are doing right now for today's lecture, you can do that as well. But I'll just be in this room on Friday evening. I'm picking time. I know Friday evening is like, what is he doing? Well, I'm trying to figure out when will most people not be like in classes and stuff like that. I know some people probably work on Friday nights. And I just had to do the best I could to take a guess at what would most likely work, knowing that if it doesn't work, I will have the video for it and you can watch it at your own leisure. But anyway, I'll do one of them on Friday night before the exam, and the other one, that says Monday the 7th. That's not right. I think this is supposed to be the 3rd and the 6th. I have to fix those dates because I think the 7th is actually Tuesday. So anyway, I have the date wrong, but the Friday and the Monday is what I meant to say there. And then this just has like an overview of the main concepts that we've talked about, like chapters 2, 3, 5, and 6. And then some important theorems, starting with the pigeonhole principle and then going to some of the counting theorems, and we've just recently done the binomial theorem and the multinomial theorem. We've got a few more things still to come that we haven't covered yet. And then I rephrased it in a different format with a sort of a things to be able to do list. So you can use this like a checklist. Just go through and apply the pigeonhole principle to applications. Solve problems involving license plates and playing cards and Mississippi problems and blah, 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 right? Solve forbidden position problems. Well, we haven't done that yet. So there's some things we're still working on here. But, you know, if you go down this bullet point list and you come to something you're like, I don't know if I know what he's talking about there, or I think I need to brush up on that, this will maybe catch that for you, give you an idea of something you might need to look at. And then, you know, the group works, of course, I just have advice about just general studying, but I also have a whole bunch of sample problems here. So if the 2 midterms are not enough, then here we go. You've got another, oh my goodness, how many is that? 14 more practice problems with parts to keep yourself entertained for a long time. Again, you don't have to do it. It's just if you have the time and, you know, hey, I love combinatorics. I do it all day long if I could. So, so there's that. And then the solutions to all of those 14 problems that I just scrolled through are also in here. So you can take that at your leisure and then just look at the solutions as you go. And then also the review. So there's also this thing called review. This one is actually like just some problems. These are the problems I am going to do at the review session. So I'm probably not going to get them all done in 2 hours, but so I'll spill over to the second session for the rest of them. So if you're wondering which problems I'm going to go over, you can look at them there. You can even try them yourself first and then listen to the review and see how it compares. You know, use it whatever is most effective for you. But anyway, you'll recognize a lot of these problems. You know, it's stuff we've been covering. So this folder is here for you. I just wanted to show it to you. I've got it all filled in, updated, a ton of stuff that you can take it or leave it, as much or as little as you really think that you can put into it. And it's just depending on how you're feeling about everything overall. Does that make sense to everybody? We got a couple weeks, so if you start looking at it right now, you're going to occasionally bump into some things. You're like, oh, wait a minute, I don't think he's talked about that yet. That's because it's probably in chapter 6. So we're going to get to that. Okay. Anything else so far about where we're at?
Is there a homework due this?
Oh, okay. So you have a homework you're working on for this week that's due on Thursday. Thursday the 25th. So there will be a homework next Thursday also due, and that'll be on chapter 6, the stuff we're going to be learning this week. And that will be the last homework that you have to turn in before the exam. So you just have the one for this Thursday, and then there'll be one more that's kind of for chapter 6, and then we'll be good. Make sense? Yeah. So, okay. Great, good question. I think that's everything. I don't have a recap on the board. There's a reason for that, which is that today we're going to start chapter 6, which is kind of a new. Whenever I start sort of a whole new topic, I, don't feel that the recap is really relevant to the new topic. I don't write it down. But before we do that, did you guys all, by any stroke of luck, happen to bring the group work back with you that we were doing on Thursday? Because I know we didn't finish this. And then I started getting my midterm resources folder together, and I looked at some of the questions that were in there, and I'm like, oh, I have some problems in there that are like number 3 on this sheet, and I don't think any group got to number 3 last time. So could we do this? And I have one extra spare copy. Otherwise, we can also pull it off of Canvas if we need to. But could I ask you to get back with your groups? We won't spend too long because I think you've already talked about a lot of this. But I really would like you to take a look at problem 3. And then once you're done with that, I have actually added a 4th problem to this group work. I wrote it down over here. It was an afterthought over the weekend, which is for you to use the binomial theorem to make up your own identity by using differentiation. So when you do problem 3, you're going to be doing integration. Because it says by integrating the binomial theorem, blah, 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 prove something. So I'd like you to do problem 3, and then as a nice sort of follow-up to that, you can add number 4, which I don't have a answer key for because there's a million right answers depending on what you might have chosen to do. So just so it's on my camera here, this is the extra item I'd like you to add. So could I get everyone to find 2 or 3 people, and we've got lots of whiteboards up around the room, and see what you can do specifically with problems 3 and 4. And I'll come around and try to give you a hand, make sure you know what's going on with this. Let's do it. Set it right here. The very first thing I would probably do with my group, by the way, is just write down the binomial theorem again. It's been a long time since we had class. Just write that down again and then go from there. You guys aren't gonna make any mistakes, right? I hope not too, because I'm gonna record this. This is gonna go all over the internet, the YouTube and everything. So the whole world is gonna know how this is turning out. Okay. So Sergio, I gotta jump in already. So you're doing the integral. I did 2 variables. Are you?
Really bad.
That's fine. So what's that? What are you doing with the y? You're treating it as a constant. I just wanted to make sure.
Okay.
Yeah, the way I,
Oh, you wanted to show already.
well, I plugged a number in first. You can do it. Yes, see what you can. All right, we got our binomial theorem written down. That looks good.
No, there's no way you have to get. Gosh, that's. I mean, it's not just. But that would be. Integrate with respect to group.
I'm sorry about integrating on problem 3. Well, I did not tell you what part of what I want you guys to think of. So it might be a case of plugging a number in for one of those variables and then taking the other one from there, or treating one of them as a constant. So I don't think that working out in there. There is a hint.
Yeah.
So the hint might help. Guys, problem 3 has a hint. Make sure you're noticing there's a hint. Hints.
Yeah. Maybe.
Yeah, I think that was my hint.
Just, that's not quite there.
Exactly.
I tutored
Oh,
too, so it's like muscle memory.
Actually,
So now we're
can I?
So differentiate.
Can I jump in here with this? But no, that's totally fine, but I think when I wrote the theorem down in my notes, didn't I do it as x to the n minus k? So if that's the case, then
Let's see
in the hint, you're going to be reverse the rules. If you want my hint to help you, you would have to calculate again. So this is, you want to just sign. Yeah, exactly. Yeah. Good, guys, good job. Good job. X plus 1 to the n. Nice. That's fine. Now, of course, there's no plus C in my final answer. So what that, before you pick up the rate. Totally okay. Oopsie. That is totally okay, but my guess is at some point you're going to think of some limits of integration that would make sense with that problem. So for right now, you can leave it as an indefinite integral, but my guess is that you'll want at some point to have some actual limits of integration there. But so far, so good. And now you have to integrate on the other side as well. So you plugged in y equals 1 on the left side, you need to plug y equals 1 on the right side as well.
No, I'm saying that there's no even. Why is also.
Brushing a lot of analysis, something a lot around here.
This case. You guys are getting.
So that's why.
Like losing how much I forgot.
So good. I like it. I like
This is
it.
thing, we have to leave it as a berry, we have to leave it as a berry. I still keep using a. Well, I mean, I'm just looking for constant fix.
It's
I
good.
guess it doesn't matter what.
Good.
Yeah.
Just want everyone to take turns.
I guess.
Yeah. See if you can take it from there. And everybody jump in if you have ideas on that. So you've integrated both sides. You didn't put any limits of integration on either side. I might want to think about whether there may be some limits to try. Because this plus C is going to be a problem. So try evaluating this from something to something, and then also at the same time evaluating this from something to something. And you can be looking at what you're aiming to get to help you decide what would be the. It's not gonna be crazy limits. They're gonna be pretty natural.
No, in
Natural. Natural.
Oh, that might be just a slip of the tongue. Yeah. See what you think. See what you think.
Oh.
Yeah.
I think
I would try 0 to 1.
Then we have to do up of one over.
So you have a plus C there. My suggestion is.
Maybe you can delete the plus C.
That gives us definite. Rather. You really need to have.
That's
Well.
so the 0 to 1 rail is for the X. So we have to change the values. I guess you could just change. Put it back. Yeah. Yeah.
I think. Oh, they. Where's this? Where's this button? Oh, actually, that makes sense. Maybe just that. Because I never.
Maybe you can get your. I like that idea.
Oh, no, but if you're integrating from 0 to 1. Yeah.
Have to do the same thing on the left. Yeah,
I guess.
Yeah, it's the right side.
Oh, yeah. Common denominator. But yeah. The 0 is actually on the rail.
Yep. Okay. See.
Oh, yeah, so.
So I'm hoping that when you do it, you have to do the same thing over here, 0 to 1. It's whatever limits you use here, you have to do the same thing on both sides. So I see that you have to do that. It's a good summation. Probably more for integration.
Yeah.
Summation on the outside.
Integrating.
Pull that outside. So I think it's really coming together pretty nicely. Yeah. Excellent.
This is fine.
Excellent.
It's how to tap it, but then there's.
Andrew. They'll tell you what to say. They'll tell you what to say. You see where this is in your formula, right?
Yeah.
It's on the right hand side, yeah? So what you need to do is figure out how does this become, I'll You're
Oh, no,
gonna go
it's fine.
0 to 1. You have to do the same thing over here that you're doing over here. So you're integrating 0 to 1, you're integrating 0 to 1. And now I want you to work on this integral. Keep in mind that integrals, they respect addition and also constants, as we know. This is a constant, this is an addition.
Yeah.
So you're gonna be able to manipulate that quite a bit. Think you know? With these guys, they'll help with it. And I'm gonna come back in
Oh, but
2
then,
minutes and see how you're coming.
Did you integrate it the second time?
No. Oh, have you already integrated?
Yes.
Oh, I'm so sorry. I'm so sorry. Yeah, I'm so sorry. Let me get myself cleared up. So this is right, but this is here. I just. didn't
Oh,
see
it's
it.
gonna be the same because.
And so then
is
this
changed
needs to be
because
evaluated
it's
in zero.
That's,
Okay. Give that a try and I'll be back. I'll be back. And you know what you're trying to get? You're trying to get the left side of this formula. So you'll know you did it right. Once you come up with that. All right, go do it. Is anything working out? No, you're plugging into.
Yeah, one first.
It makes a lot more
So
sense.
that denominator is still.
Yeah, well, with all the summations.
Keep your summation.
Oh.
Summation.
Ah, still-
Yeah, I mean.
It's depending on different.
We have to subtract.
Yes.
I am like a high school student.
Look at that. You see that anymore on column 3?
I teach, we're trying to get,
So that's starting. to-
You have that. so start writing out the summation. So you get to like.
Have this.
Looking good, looking good. It's working out a little better now?
Sweet. Okay, cool.
That's how we get.
That's really good. That's actually,
Yeah, well,
that's showing up.
It's
on-
our right side.
And then
It's the other side.
Try to bring this up.
Okay.
Uh,
Zero.
Well, then, yeah.
One.
When we integrate this. We just plug in one, it's one, I don't plug zero, zero.
Yeah.
It used to be one.
Oh, no.
This whole thing's.
No.
But there's a, there's still this. Yeah.
Yeah, this is considered constant.
Yes.
It's us bringing about.
And this is actually 1 over WC. Which is actually going to be.
Okay.
No worries.
Oh, no, there should just be one.
Let me leave it at me.
Is it working out for what this thing said?
Yeah.
Make sure that your whole thing is.
For the last part of the summation, where we get to k equals n. For our formula, it should just be 1 over 1, basically.
Yeah, this is great.
Like in this last part, it's n choose n times 1 over 1.
Now,
Put in.
you got a 1 over n.
That, so let's do 1 over n.
N minus N minus.
But actually, this term doesn't make me too worried.
Yeah.
Let's write down these, let's check it. for a couple more
Yeah,
times.
okay.
I think it's going in the right direction.
That's-
Okay.
But then that one.
Did this come out to anything good?
I think so. I have a question.
Okay.
So on
I-
your
yeah.
sheet,
I
you
have
have
it.
the last part of the summation.
Yes.
N choose n times 1 over n plus 1.
Right.
But if k equals n, shouldn't it just be 1 over 1? So 1.
If K is, should be 1 over 1, but the thing is, these terms could be in a different order. Let me show you what I mean. So, first of all, is this supposed to be n choose
And like,
1?
again, like, if we did it the other way, then.
Is this n choose 1, n choose 2? This should have been n choose, this is where K equals 0.
Oh, so we integrated so that. we did
Agreed.
this.
Now, I think you're all comfortable with the idea that n choose 0 is the same as n choose n.
Yes.
And would you be also comfortable that n choose 1 is the same as n choose n minus 1? And and that n choose n is the same as n choose 0? Let's just remember, guys, this is one of our really important identities. N choose R is the same as N choose N minus. If I have 12 players and I have to choose 5 for my team, instead of that, I could choose 7 that are not on the team. And it would be equivalent, because as soon as I know who's not on the team, then I know who is on the team. As soon as I know who is on the team, I know who's not on the team. So this is completely symmetrical. And now, I believe this is gonna be exactly what she has. So that was just because of the way this was indexed, I believe, that you had. It wasn't that you did anything wrong. This was just the way it was sort of indexed in the first place. Okay. You okay? The idea is to take the binomial, plug a number in, I basically following him, plug a number in for y, then integrate both sides. Now, it didn't tell you what limits of integration. You have to figure that out. But once you do that, you just integrate the left side, integrate the right side, and you see that, well, they have to be the same. Yeah. It's kind of, you know, we haven't used a lot of calculus in combinatorial, and they don't generally get brought together very often. So I thought this was kind of a neat way to prove an identity involving binomial coefficients, but which requires calculus to do.
So something that changed that.
The limits of integration?
Yeah.
You'll derive a different identity. It's not the one I'm asking you to prove, but you'll prove something. You'll prove some other formula that would be a great way for me to write the next test. Right? Is that I'm just gonna take this and instead of integrating from 0 to 1, let me integrate from 0
Yeah,
to
I
2.
think part of it is kind of
And then I'll have a different thing on the left and I'll have a different thing on the right, but again, it could be derived by the same general principle.
So our limits have to be 0 and 1 to get this problem
To
right.
get this one to work,
Is
yes, so that was the trick. I mean, what I was hoping is just that people would naturally try that first.
Oh, it is.
Because it's kind of the nicest limit. So you're plugging in numbers that have powers. 0 to a power is easy, 1 to a power is easy, any other numbers, then suddenly you have something messier, and kind of looking at how clean this formula is. You're probably going to steer clear of it.
I think the good thing is,
So there's no actual,
If I had seen some plus minus going on here, I might have thought about using a negative one. Because -1 to a power would alternate positive, negative, negative, and that would have been, you know, an idea, but you have to tinker
Oh, I
with
get
it. This isn't something you just look at and say, oh, I know how it's gonna work out. You have to actually write it down and just experiment a little bit. That's part of what learning is all about, especially in that.
so nothing actually indicates those bounds, just like you have to look at it and kind of feel it out.
Feel it out. Exactly. So try to see if you can, instead of doing an integral on this thing, you can make up your own formula by using derivatives instead of it.
Oh,
See what you come up
I-
with. And there's no right answer. There could be lots of,
No,
I mean, there's no right answer, there's also no wrong answer. It's just whatever you come up with.
Go for it.
Anybody need an idea? How are you guys doing back here?
All right,
I guess I'm curious because.
Ah.
Then-
You know what?
After looking at your,
zero factorial.
I guess.
Well,
It's all good. It's all maybe I'm so used to this from other.
that's you start not too bad.
And I just think like, oh.
Yeah, that's just seeing you do it now. It's like,
And choose three, and they say.
Oh, actually, it's really great on like.
that was years ago. No,
Like, you have,
like a different college.
like,
Like,
you can do everything and be like,
I'm meeting with like, the other day. I was like,
And minus five, I'm gonna see those.
you remember Littles? You're not allowed to use Littles. They haven't learned ribbons.
Because people.
So like anytime I want to jump in on top, I'm like, wait, no. You can't just say,
Okay, let's.
Yeah.
it is for limits, but when they first teach limits, like they teach it out, but it's not written, it's like. And so they teach limit.
Yeah, he.
They can't do the models, they can't like compute limits.
By the way,
using
before
the. Yeah, that makes a lot of sense.
When they're just providing an identity, Then the one. that's-
Yeah.
All I have to do is I start with this. Say, plug in a number for.
Yeah, like, and I'm just sitting there watching them, like, slowly solve it. And I'm like, it's powerful, it's fine, it's powerful, please. It's weird, it's like the start of it's really, but later on they get into stuff. Like they do like wonderful integrated, like they have to.
Wait, so is there like a business?
No, it's just this, I mean, I assume there probably is a thing after. Yeah, but I just know.
Anybody need a hand? Did this?
I mean, I just talked to their first
Good on that?
today, and
Okay, and then you did, you
first,
basically made up your belt, so you plugged in.
the first like 4 questions were one.
Actually, you just did
Basically,
differentiation.
it was like,
And then you plugged in.
plug, like literally like f of x of this function, what f of 2.
Other than
Oh,
the problem, you get this.
And then it
Oh,
was like,
interesting.
what's the derivative of it?
It would be the same.
What's
It would be
Okay.
2 with the derivative? Like,
interesting formula for sure. I got some nice
Yeah.
formula for. In.
I just heard like it's supposed to get harder for them later on, but I feel like it's for business majors, not harder for us. I mean, I'm not expecting them to do this hard, sorry.
At most, and people, it does have.
It's just funny watching them like
And then for each
complain,
other.
or like they'll ask me like, why did x squared become 2x? Like they.
And all the power over himself. Yeah, so that's one side. Hey, well, okay, it'd be the side. And, maybe it's actually never my mistake, sure, so you first choose the committee, and then from the committee, you choose the president, and the size of that committee could be. So you actually, not only did you make up a nice identity, you gave it a great testimony. Give me a comment.
Okay.
Like, you guys would be able to prove it. There's another one. Doing essentially in terms of committees. This is really neat to see. How something that is-
We do have to differ, the last one, like,
can
we start
be
going.
explained
Yeah.
Generally what it's like.
I really like Yeah.
Like,
And so you can do
it
this all
pays
day.
out. Or not the 0 percent, I guess the end. Although you're already on security.
I'm not sure if like keep this as 0 or
And
make
then I
it
suddenly realized that.
Because, because like when you do Taylor series and you differentiate in a summation,
Plus minus.
you always add 1 to the
Yeah, I know.
right?
I think it might be, you might only go to n minus 1.
Manipulated somehow, and I stopped with our.
Because if we have
Yes,
this,
n minus 1.
it's basically n minus 1 minus.
But yeah, that does work.
Sorry,
pretty well.
n minus 1.
Anyway, good job. Let's study.
Just to make sure like.
Just like-
It's still,
well,
it
what
should always be
you do,
bigger than equal to
actually
0.
what you do.
Yeah.
Like,
Study. You challenge each other, you each.
then
go off
n
the
minus,
backfield there.
and that's 0.
Don't tell all the
Plus
partners
one.
what you want to do, but you.
Minus
give it a
one.
number.
Yeah.
It's 0. Okay. So
Yeah,
you're
yeah,
right.
yeah.
So it is 0.
That-
Yeah.
yeah.
During the appointments.
Because if we left it
And
and
you're
moved it
studying.
Yeah, yeah, yeah.
next to the negative.
Sweet.
You can't do there,
Like that.
you each see if you can know each other's,
Before he
uh,
writes the marker.
by any means, by no middle here, by combinatorial or whatever. See what we're going to come up with. I think that would actually be a neat way to
Do
study.
you think we do
What's that?
n minus 1?
I think so, yeah.
Yeah.
Working on, oh, that doesn't make sense.
It'd be a good way to have a nice dialogue
Thank-
interaction about a topic that kind of stands across some of it.
Because,
Still combinatorial identity.
because when you subtract 1 from here, there's a chance you're like starting at 1. So you have to.
Totally okay with identity as a. Make it hard by putting So if you said I'm gonna let X equal. Then you have n minus 3 and minus 1. You'd have a
Oh,
lot,
right.
right? And that's everybody in the room. So you can say like this. And, yeah, kind of my brain is always sort of. I mean, there's.
Right?
Ideas of like how to.
Power of zero?
Yep.
So that we actually
Three
of them. I mean, it's the same thing that a lot of like, give like a tiny little. No order. It's like.
I just thought of a really neat way for you guys to study for your exam. All you need to do is find a study. And both of you start with separately, start with the binomial theorem and an identity by doing kind of what you're doing right here. Anyway, this is all great. In fact, you could stop here if you want and say, here's my identity. But you do all this scratch work and you derive something. And
Number of
then
like the mountain.
show it to your study buddy,
Plus the number of-
and you ask them to try to prove it.
But then I was like.
And they do the same thing for you. They start with the same thing, they make their own, it'll probably be something different, they hand you theirs. And you each try to prove each other's identity, using the binomial theorem. Or you could prove it a different way. If you plug in, I like your identity, can I hijack this, conversation just a little bit? If I plug in X equals 1 now, if I plug in X equals 1, I'm gonna get this on the left side, which is fine. And on the right side, if I plug in X equals 1, I'm gonna get, you know, a bunch of terms here. And minus 1, choose, and minus 1, I guess. I just put in X equals 1, and I can ask myself, so this is what you hand your study buddy, and you ask them. Now, I'd like to point out, by the way, this left side. This is the number of committees that can be made out of n people where a president is selected. You have n people available, you choose one of them to be a president. What do you do with all the other people? Or you either put them in the committee also, or you leave them out.
Out of all the different types of.
The size of the committee could be anything, depending on whether it's thumbs up or thumbs down for each individual person. So this is literally, a lot of our combinatorial identities that we did last week, we were doing committees of a certain size. That's not what this is. This is just committees that have a president made from possibly n up to n. And so then the question would be, well, how can you interpret the other side of the equation to be the same thing?
Like, there's that.
So you should be able to explain this as being committees, where you have a president. So you choose that president, and then out of everybody else, you either choose all of them, or you choose all but one of them, or you choose all but two of them, or you choose nobody. Think of it in those terms. So it's kind of neat. There's no right or wrong formulas here. Like, we could do this all day long and have all those different ideas.
Where was the president years ago?
Like the first 5.
That is an excellent question.
Oh, yeah. those-
So I have to just
But then
check
if I
that
actually
we
get
get it completely right.
I'm trying to become more. Oh, it's gonna get like. a lot.
This, how does it go from here to here?
What?
Driving this.
Now, if I take the derivative of that, I'm gonna get n choose k, and the derivative of this would be n minus k times x to the n minus k minus 1. Are you missing this? So that needs to be in there, so this is not quite. Well, you know what? you caught it. Because
I'm like, yeah.
not because you saw the outcome, because the combinatorial argument. You're like, wait a minute, this is supposed to be committees that have a president, and over here, where am I getting the president? So I like that. Good job, guys. I like it. Hey, guys. Hello. Could we, I know not everybody's totally done with their conversations, although it looks like, most of you got a good progress on those two problems. I think I'd like to bring us back together so I can talk about something else right now. Don't forget that the solutions to these group works are also in Canvas. But that problem 4 that we just did has no, right or wrong answer. There can be as many different, formulas that we can make as there are people in this room. So it's a little bit of an open-ended challenge. So, does that all make sense to you guys? Okay, that's okay, I'll get it. I got it. This is what they pay me the big bucks for. Let me grab my camera here, and we are gonna spend the second half of our class today talking about the next chapter. Chapter 6. Yeah, I would like to start that. Does that sound good?
Yes.
This is called the inclusion exclusion principle. So let's get into it here. Chapter 6. I just love this stuff. Oh my goodness. I always try to ask myself, what's my favorite part of combinatorics? And the answer is always whatever chapter I'm on at that moment. I really like it all. So inclusion, exclusion principle. Okay, so this fits right in with some of the other principles that we've looked at in these first few chapters. Let me give you an example to kind of warm you up with this topic a little bit. So maybe I have a problem like this example. Just to get it going. How many strings, we'll ask a question. How many strings of 7 letters have, sorry, not have, sorry. How many strings of 7 letters, sorry about that, start with a vowel or end with an M? How many strings of 7 letters start with a vowel or end with an M? And it is so important, guys, to watch these words. This is one of the downsides of combinatorics, is the choice of words can dramatically change the meaning. If this says start with a vowel and end with an M, it's a totally different problem. Okay, so visually, I like to draw my slots here. Those are my 7 slots. But what I'm going to do is I'm going to figure out, well, how many strings start with a vowel? And then I'm going to figure out, well, how many strings end with an M? And I'm going to count both of those individual problems first. So let's actually solve this. So for my solution, the number, I'll use the pound symbol for that, the number of strings starting with a vowel. So I'm looking at my 7 slots and I'm gonna put a vowel in the first slot. How many vowels are there? 5 of them, right? So I have sort of 5 choices, so 5 choices, I put my number of choices in the slots. And then the rest of the slots can be anything. There's no constraints right now. So 26 choices for our regular alphabet for all of those slots. And so the answer is 5 times 26 raised to the 6th. Right, okay. So that's part of what the question is counting, but we also want to know, well, how many strings end with an M? So let's do another line for that. Number of strings ending with M. Okay, so I've got my first case here, so to speak. In this case, well, you can kind of maybe I'll draw my slots again one more time, but this is pretty clear that that last slot, we don't have a choice. It has to be an M. But the other 6 slots are wide open, right? 26 to the 6th,
Yes.
right? So 26 choices all the way across the rest of these slots again. So that would be 26 to the 6th. So ordinarily, what we would do is we would sort of treat these as 2 cases. And the way we handle cases normally is by using the addition principle. So what we would do is, okay, well, how many strings started with a vowel? And then how many of them ended with an M? And then what's that grand total? And you would add them up. But what's the problem with that?
Double counting.
Yeah, we are double counting. Some strings are going to be listed here and here, even though they really only constitute 1 string. So a string that ends with an M, but also starts with a vowel would have been credited both here and here. And so in the grand scheme of adding everything up, it was added twice. What we have to do is subtract it back out again. So what we are gonna do, guys, is we must subtract. This is where the inclusion exclusion is coming in. We must subtract strings in both categories, i.e. strings starting with a vowel and ending with M. And does anybody want to tell me how many of those there would be? 10?
5 times 26 to the 5th.
Yeah, see now this first slot, if it starts with a vowel, would only have 5 choices, but you also don't have any choices on the last slot either. So you have 5 slots in the middle that have 26 choices each. Other than that, you're cut down a little bit from what you had before. So that would be the amount of strings that are being double counted. And so my final answer, can I write down here, guys? It's okay, I'm gonna write just right here on the bottom, just briefly. My final answer would be to take 5 times 26 to the 6th and add that to 26 to the 6th, and then subtract 5 times 26 to the 5th. And that would be a final answer, and it would be okay. Some of you might be looking at that thinking you could do some factoring or simplifying of it, but it's almost nicer to leave it like this so I can see all of the terms that went into the thought process of the answer. Does that look okay? Questions on that? So we can formulate this a little more in a set theoretic way that would then be, applicable to a more general situation. I'd like to show you that as well, just from a notation perspective. So let me just quickly formulate this same example with sets. Right, so I'm just gonna create some sets for this. So it might look something like this. I could create a set capital A, and this would be the set of 7-letter strings starting with a vowel. So that would be the set A. And then we make another set, which would be B. I'm gonna do it right below it. I'm gonna use this little ditto symbol so I don't rewrite everything every time. But this is the set of 7-letter strings ending with an M. And so then if we phrase it this way, then what we want to find is actually how many strings are in the union of these 2 sets, yeah? So I'm gonna make a union of A and B. I wanna look at the size of that. And if you kind of believe what we just did in the actual calculation, we figured out the size of A. Right, the number of strings that started with a vowel, then we figured out the size of B, which are the number of strings ending with an M. And what we did is we subtracted those strings that are in both places, both A union B, A intersected with B. So the Venn diagram picture, you guys have probably seen these before. You put your two sets like that and you can see that the intersection, anything that belongs in that intersection is getting double counted. Okay. So far, everybody with me? Gonna make it a little more complicated now. Let's go back to the example, but I'm gonna make an extra bit of complication here. How many, ask another question. How many 7-letter strings? How many 7-letter strings start with a vowel? So start with vowel. End with the letter M. Or contain the word kitten. So add one more part to this. So now you see that we have sort of 3 conditions. And I'm gonna kind of milk the notation that I've already been using. So we're still talking about 7-letter strings. You still have sets A and B that are relevant here, but I'm going to answer this, I'm going to create a 3rd set, I'll call it C. And C is going to be the set of 7-letter strings containing kitten. Right, and in this case, what we want to find. What we want to find is the size of the union of all 3 sets. So any string that's in A or in B or in C. Okay, so this is going to be the idea. Let me show you, this is hard to take notes on, because it's kind of it's a proof that's in action. But if you just want to watch, it's okay. But I'm basically gonna draw another Venn diagram to kind of get this started. And I'm going to imagine that I would like to count everybody who's in the union of A, B, and C exactly 1 time. The first thing you would probably do, if I'm following the model of what we did before, would be to add up all 3 of the sets individually. Okay, and now I'm gonna show you what I mean by it's hard to take notes. So the size of A, as I count that up, anybody who is in any of these regions that I've labeled with 1 has been counted 1 time. Right? Now I'm gonna count everything in B. So things that are in this region are getting counted for the first time. Things in this region are being counted for the first time. But this is now becoming a 2, and this is becoming a 2. I am recording this, so this will be proof by video. You sort of see it evolving as we go along. Then I go to the set C, and all of the regions that are inside of C sort of get bumped up by 1. So everything down here is getting counted for the first time. Now everything here is being counted for a second time. But here's 3rd time and 3rd time, right? Too many.
What is that one up top 2?
Oh, I'm sorry. I didn't mean to do that. This one is not being counted. That's still only a 2. Yeah, okay. Right, so that's how many times everything has been counted if I just do this. So I've actually triple counted things that are in all 3 sets. Makes sense, right? So I now have to start, the idea would be to subtract some stuff. And I could subtract the size of A intersected with B. Okay, so then I'm gonna go back to my proof, and I'm gonna take the A intersect B regions and drop them down by 1. So the 2 and the 3 here in the intersection of A and B go down to a 1 and a 2. Okay, and I can see that I still have too many things being counted. I'm gonna do more subtraction. I'm going to subtract the intersection of A with C, which is actually these two parts of my Venn diagram. So this goes down to a 1, and this one also goes down to a 1. And I almost have it right, but there's one little section that has been double counted, so I'm gonna subtract the intersection of B and C. And that'll get this 2 down to a 1, but now unfortunately, the 3-way intersection, it got added 3 times in the first 3 terms, but then it also, anything in there got subtracted 3 times. So I now have to go back to a plus again and add back in that 3-way intersection. And now this is how the diagram is supposed to look at the end. Every single string that would be in every single region of this diagram has a net total been counted 1 time. That kind of makes sense? Yeah, so what kind of numbers do we get out of this? Let's see, so for our example here, the size of A, we already worked some of these things out. The size of A was 5 times 26 to the 5th, right? And then we add that to the size of B, which was 26 to the 6th. Oh, I'm sorry, should have been 5 times 26 to the 6th, right? Plus 26 to the 6th. And then the size of C, we haven't worked that out yet. How many strings of length 7 contain the word kitten? What do you think? 26 times 2. I could either have kitten with 1 extra letter on the end of it, there'd be 26 of those. Or I could have 1 extra letter at the beginning and then the word kitten, right? So this is gonna be, for the set C here, you're gonna have, either kitten. And then you have 26 choices, or you're gonna have 26 choices and then the word kitten. If that makes sense. Right, so that's actually just 52. You just add up those 2 cases, you just get 52 for the size of C. Okay, now we're gonna subtract the intersections. How many strings start with a vowel and end with an M? Well, that actually is the A intersect B from before, 5 times 26 to the 5th. I'm gonna subtract 5 times 26 to the 5th. And now we have some new things to calculate. I have to figure out A intersected with C. So how many 7-letter strings start with a vowel and contain the word kitten? Hmm? 10. It has to start with a vowel. How many vowels are there? So if it starts with a vowel, it starts with an A. So it's either A kitten, E kitten, I kitten, O kitten, or U kitten. That's it. You can't do anything else, right? You have to start with a vowel and you have to have the word kitten there. So this is just -5 for that term. And I'm doing them in order, by the way, of the way I've listed the ordering here, which is actually a good ordering to do them in. It's kind of in alphabetical order. And then we have B intersected with C. So how many 7-letter strings end with an M and contain the word kitten? Well, just 1. It's kitten M. That's it. So there's -1. And then finally, how many 7-letter strings start with a vowel, end with an M, and have the word kitten in them? You can't do it. You can't do it. You don't have enough spaces. Kitten is using up 6 of your 7 spaces, and you'd have to add an M on the end and a vowel at the beginning, and that's too many spaces. So yeah, there's nothing else to add there. So this would be the whole answer right here. Okay. I bet that if I asked you to, do you think you could write down a 4-set version of this inclusion-exclusion principle? Why don't you try it while I'm erasing the board? Okay. Oh my gosh, I have to erase that.
Hey, I offered.
I need to have like a ladder. to get here. What group was this? Jeez. Okay.
No.
Are you taller than me? I guess you are. I guess everybody's taller than me. Oh, wow, okay. So for the 4-set version, we'll have obviously a lot more terms. I guess I'll write it down and then we'll try and get to a general. I want to eventually get a general formula. Is this, what we're talking about here, guys, is the inclusion exclusion principle. So there is a 4-set version. So this would be something that's giving a formula for A, union B, union C, union D. Now we have a lot of sets here. I won't do the whole in motion proof this time. I'll just start writing out what would be reasonable terms. First of all, it would make sense to add up all 4 sets individually. So the size of A, give yourself plenty of room, by the way. I should have warned you ahead of time, especially if you're using paper. Make sure you have enough room because there's going to be quite a few terms. Those are the singletons, the individual sets. And then as you can kind of get the idea from the pattern here, you're probably going to need to subtract all of the 2-way intersections, right? So I'll go to a new line for that. I have to subtract A intersected with B. I have to subtract A intersected with C. I have to subtract A intersected with D. And I'm doing these kind of in alphabetical order. I'm doing all of the A intersections first, and then I'm done with those. I go on to B. So B intersected with C, and then B intersected with D, and then C intersected with D. And we see from the last example that we then had to add back in the 3-way intersection of A, B, and C. And actually, that is what we have to do here as well. So I'm going to go back to plus. It kind of alternates plus, minus, plus, minus. For the next one, we have the 3-way intersections being added. So A intersect B intersect C. And then we're going to add the intersection of A, B, and D. And then we'll do the A intersect C intersect D. And then we will add B intersect C intersect D. And if you were taking a wild guess, what else would we now need to do? Subtract. Which one? The 4-way intersection of all. So just like here, we stopped with the intersection of all the sets. Here, I would not be surprised if we would need to add back in the intersection of all 4 sets. Exactly. What is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 terms. Oh, how many questions are going to be on the exam? Oh, there's only one. Has 15 parts, but anyway, no, I'm just teasing. But you can see how somebody could turn this into a problem that would take an hour to do. Right? You might have a lot of terms to calculate in theory. Okay, so yeah, that's how it works. Let me write down the general inclusion exclusion formula. This is a pretty important result. And let me actually come back over here so I have plenty of room to write it down in abstract notation. Okay, so let's do this, and then maybe we'll just practice with another example and call it a day. And this is actually stated in the book as a corollary. So I'm going to write it as that corollary. So this is corollary 6.1.2. And this is the inclusion exclusion principle. I'll just call it the IE principle for short. And what we're going to do here, guys, is we're going to take an arbitrary number of sets. Okay, so it would look something like this. If A1, comma, A2, comma, dot, 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 up to AM are sets. Then the size of the union of all of them. So this is the union of A1 with A2 with so on and so on up to AM. And what it's going to be, guys, is these alternating plus minus contributions, just like what we see in the 4-set version. We'll start by, I'm gonna write them as summations here just to save a little space. We'll start with the summations of just the individual a sub i's. Now, when I'm doing that, of course, the I is going to go from 1 to M. So it's a summation with I going from 1 to M of the size of a sub I. Then we're gonna have to do a subtraction. And we're gonna subtract a bunch of things that will be added together as well. This will be a summation of the intersection of AI with AJ. So I'm gonna write it like that, and in this summation, basically what we're doing here, guys, is we're gonna have 1 less than or equal to I, less than J, less than or equal to M. I'm gonna write my summation like that. So the I and the J have to be different. They're not allowed to be the same, and I don't want to subtract A2 intersect A3 and also subtract A3 intersected with A2. That would be double subtracting. It would be as if over here, you notice over here, I don't have a term where I did D intersect A. Because I already did A intersect D, but there's no reason to write them in the opposite order. So what I'm basically saying is I might as well just assume that my first subscript is less than my second subscript. Just kind of as an arbitrary choice, okay? Then we're gonna go back to addition again. And we're gonna add up the size of the intersection of a sub I intersected with a sub j intersected with a sub k. And this time 1 is less than or equal to I, which is less than j, which is less than k, which is less than or equal to m. Again, 3 distinct subscripts. And we might as well put them in increasing order. Okay? So we have that. And then finally, then we have minus, and I'm just gonna put dot, dot, dot here. And then we finally get to the last term. The last term is the intersection of all of the sets. We have to be careful about whether we are adding it or subtracting it. We noticed that with the 3-way intersection, we needed to add the last term. But with the 4-way intersection, we were subtracting the last term. It seems to depend on the even or odd parity of the M that you have, right? The number of sets that you have. So actually what it comes out to be is -1 to a power, and the power is actually M plus 1. And then times the size of the intersection of all of these sets. Just for a quick little gut check on that, if M is an odd number, then we're gonna finish with a plus sign. That's what happened right here. 3 sets, we finished with a plus sign. But if M was an even number, like over here, 4 sets, we finish with a negative term. So it just depends on whether the set is even or odd. Okay, everybody good? I got 5 minutes left. I'm gonna do one more problem. It might have 15 parts, but we'll get it done. It won't be that bad. Okay, so one last example. This is also just good review of the earlier material. This time I'm gonna go back to poker cards again to make my example. These are so much fun. How many 5-card poker hands contain exactly 2 spades at most 1 heart, or there's that word, or a flush. And for those of you who don't go to Vegas regularly, a flush just means all of the cards are in the same suit. So it's all hearts or all spades, whatever, so all same suit. Okay. So let's see if we can just do this one with the, we don't have a lot of time, so I'm gonna go through it fairly quickly. I'm gonna make sets again, right? So capital A would be the set of hands with exactly 2 spades. This is mostly just review of the old material now, we just have to incorporate it into our inclusion exclusion principle. The second one is the set B, this is a hands with at most 1 heart. And C is the hands that are a flush. Last example for the day. Let's just see how this works out. What we're really trying to count is we really want to find the size of the union. So there's only 3 sets here, so it won't be 15 problems. It'll be more like 7. But a lot of these are gonna go fast. And we've done problems like this before. Let's actually just write out the general formula one more time. The size of the 3 individual sets are gonna get added together. And then we'll end up subtracting the 2-way intersections. There's 3 of those as well. And then we'll add the 3-way intersection of all of them. Okay. And from here, most of the rest of this is just reviewing the counting strategies from the earlier chapters. Just pull this up here a little closer. Let's just kind of go through these 7 things, like 2 minutes to do 7 problems. It's not real good numbers, but I think I can do it pretty quickly. Hands with exactly 2 spades. So you know what you're gonna do? You're gonna pick your 2 spades. There's 13 choices. I choose 2 of those. We don't care about the order when we're doing poker hands. So I'm just choosing them. And then out of the other 39 cards, I have to choose 3 of those. So those are the 2 subtasks. Choose 2 spades and choose 3 non-spades. Okay? I'm only looking at set A. What about set B? Hands that have at most 1 heart. This is well suited to, well, you could say, well, there's either 0 hearts or there's 1 heart, right? So you can just take that as cases here. So the hands that have 0 hearts, oops, I'm sorry. 0 hearts would be, all right, we got 39 non-hearts, choose 5 of those. So from the diamonds, clubs, and spades, just choose 5. The other option with that same case is, what if we had exactly 1 heart? Well, then we'd choose 1 of the hearts, and out of the other 39 cards, we would only choose 4 of them. Because we've chosen 1 heart and 4 non-hearts, okay? Let's do the next one. Again, I'm going kind of fast, sorry about that, but we'll get through this. The number of flushes. They all have to be the same suit, so what kind of choices do I have to make? Which suit? That has 4 suits, I choose 1 of them. Once I have that suit chosen,
You have 13.
I gotta pick all of the cards from the 13 in that suit, so 13, choose 5. We're good? Okay, those are the first 3 terms, now let me do the intersections. Should go pretty quickly. So hands that have exactly 2 spades and at most 1 heart. So I'm gonna choose my 2 spades again, 13, choose 2. And then I have 3 more cards to pick, and I can either pick no hearts or I could pick 1 heart. If I pick no hearts, then that means I'm going with the diamonds and clubs only and choosing 3 of them. So that would be 26, choose 3. Or I could choose 1 heart, there would be 13 hearts to choose 1 from. And then from the diamonds and clubs, I would choose only 2 other cards. You with me?
Yep.
Cause I already got the 2 spades, now I'm just choosing 3 other cards. A good thing for you guys to do maybe later tonight is to actually just go back and write little reasons for each of these. I'm not doing that here because I'm kind of running short of time. But that's A intersect B. How many poker hands would have exactly 2 spades and also be a flush? Okay, guys, let's be careful. A flush has to be all 5 cards are in the same suit. And we're saying that we have to have exactly 2 spades. Is that possible? Exactly
I see,
2
exactly
spades
2 spades.
cannot be compatible with a flush, right? 0. That's a 0, that's a 0. And actually, if that's a 0, if intersecting those 2 is 0, then you know that when you intersect all of them, it'll also be 0. But what about B intersect C? At most 1 heart, but it has to be a flush.
0.
At most 1 heart could be no hearts. At most 1
Oh,
heart could be
yeah.
no hearts, which means we could have a flush. It's just it would have to be a flush of clubs, a flush of spades, or a flush of diamonds, right? So I would have 3 choices. Oops. I would have 3 choices, not 4, from which to make my flush, right? So it's similar to what we had before, but now I have to throw out the hearts. Okay. And then it's impossible to have exactly 2 spades, at most 1 heart and a flush. So that would be a plus. So there you go. We got to practice 7 counting problems in 5 minutes by doing the inclusion exclusion principle. That's the whole shebang. I am over time, so I'm gonna stop right now. If there's questions on this, maybe after class, you can come up and ask me real quick. But I'll be downstairs later on. If you're working on the homework and want to talk to me about it, feel free to drop by. I'd be glad to speak with you then. Have a great rest of your day, everyone. And bye for now.